So welcome to the first tutorial of the day. Thank you, Tilman, for the introduction. So I will tell you about a few basic concepts about texture analysis, starting with basic crystallography up to texture tomography. Some concepts will probably be very familiar with many of you, but please bear with me. So just a short overview. I will talk about for what materials texture analysis is important. We go a bit into crystal structures, how they're defined, and symmetries of crystals. We advance to orientations in 3D, which is basically the topic of the workshop. Go to orientation distribution functions, which are very nice for describing texture. Then and I'd make the link to diffraction and the end, how this comes together for texture tomography. So texture in general is a property of polycrystalline materials. So here is a sketch of a material. We have these crystallites, which are arranged in whatever other matrix around here. And what is important that we can define, for example, an orientation based on the crystallographic axis of the crystal. And then if we want to do some basic analysis on this, for example, we can take the b-axis, and we see that all the possible orientation of this b-axis are here on the circle, for example. And if we look a bit at the sample, we will immediately see that the likely orientations in the sample will be in this wedge here. And we can also define probably some preferred orientation. So where is this important? Many materials have this kind of distributions of orientations. One big group are metals, ceramic rocks, where we have very densely arranged grains or crystallites that can have different orientations. I chose this picture here. We have really flat grains because often in this kind of material, texture comes about due to the manufacturing or deformation afterwards that induces a kind of preferred orientation into the system. Another big group of materials are hierarchically biomaterials, in particular biominerals. So for here, the arrangement works a bit different because it's a combination of organic material and crystalline materials. And they are hierarchical because we see that they are very organized in several length scales. Here, for example, we have the overall shape of a bone. Inside, we can find these osteum bone tubes. And in a circle around these tubes, we find the collagen fibrils, which have crystals, so hydroxyapatite particles embedded, and these again will have a preferred orientation due to the growth, due to how this material grows. Another material that I will show you, just because we will use it this afternoon, is silica biomorph. Well, it's a completely inorganic material. It's synthetically grown, and it grows in these different shapes. So it makes very different shapes on a micrometer scale, and they consist about they contain this barium carbonate nanorods, which are embedded in amorphous silica. And we can see here already here in the TEM image there is some arrangement of these crystals which are probably kind of textured. So this we are going to construct this afternoon a piece of such a helix. So just as a little spoiler. So let's have a look at what is a crystal and what is a crystal structure. Here we have a simple unit cell of, again, like this barium carbonate structure. And a crystal in general is defined by a repetition of this unit cell where we have a specific arrangement of atoms. So we have in different colors, the barium, the carbon, and the oxygen, for example. And we can define a cell that repeats each other in space along these three vectors, which define in which direction the cell is repeated. Another important property of crystals is the symmetry. And there's several ways on to classify crystals. One important thing is the crystallographic point groups. So there's 32 in total, and they contain the symmetry properties of a crystal. So in particular, rotations, reflections, and inversions around the point. Just to go a little bit into detail, so the simpler ones here, you can see that, for example, here is marked by C2 or number 2. It means that we have one rotation axis with a two-fold symmetry. So if you rotate it by 180 degrees, it will look the same. The same that's here, we have a 4, so it's a four-fold symmetry around the same axis, which goes into the projector plane here. We have 3. And if there's a second number in this notation, for example, here 422, then we have a secondary axis. So we have one with a four-fold symmetry, but we have another 2 axes with a two-fold symmetry, and then there is more complex systems. What is important in the following for describing orientations, we don't need to take care about reflections and inversions. So where you have an M here for mirror plane, for example, this will not give us, our techniques will not be sensitive to this. So what is important, we have proper point groups, and there are 11 of them, and these will, as we will see in a moment, affect our orientation space, actually. So let's go back to the barium carbonate. We have this 2-2-2 point group, which means we have 3 axes where we can do two-fold rotations around. And if you imagine here, this axis, for example, we can rotate, and this will move all the way up here, and it will look the same. Then, of course, this unit cell is repeated in space, so there's another classification by the so-called space group, where we add lattice translations and other more macroscopic properties, because depending on the point group, you can see that for some of them, there's more space groups, so there's different ways how to arrange the unit cell in space while keeping the same symmetry as defined by the point group. And these have a number that goes unto 230, and if you, it will be important for later for text tomography that you're aware of what is your space group in order to simulate the right crystal. So let's talk about orientation in 3D. So in 2D, orientations are quite simple to imagine, right? We can just have one arrow that points in one way. In 3D is not so straightforward because we have 3 degrees of freedom. Take a coffee cup here because it's a nice object that has no symmetry properties, no orientational symmetry. So if you have this state, for example, you need to rotate by 360 to get in the same way, and also in all different orientations. But we see we have 3 degrees of freedom. We can rotate around this, and around this. And if we want to define now an orientation, what is important to notice, we cannot just define a vector, like for example here in standard spherical coordinates define a vector by 2 angles, because if it just points in this way, let's say, sorry, no. Then it still has this degree of freedom, which is not defined by a single vector. So we need a third. We need a third parameter to completely define orientation. And there's several ways how to do this. One way is the axis angle rotation. So there's different ways also to parameterize this. I will refer to Julien Flamand's talk tomorrow for this. So how does the axis angle parameterization work? We define a rotation axis here in blue, which is defined by two angles, for example, or it's just a unit vector. And then there's the rotation angle, which defines how far we turn in this direction. So to demonstrate this, for example, with two coffee cups, we have a reference orientation, which would be this, for example, and we want to go here. Then we can, we need to define an axis that goes somewhere through here, for example, and then we can rotate, do a single rotation around this axis, and we will arrive at the same orientation. So if we know this, how we parameterize our orientations, we can define the orientation space. So all possible orientation for this kind of object. And it turns out to be a sphere because, so we will define a point, for example, here. So the direction from the origin will be the direction of the rotation axis, and how far we go from the origin defines our the rotation angle. So the diameter in the sphere is consequently 360, and the point here on the sphere will be the same as on the opposite side, because if you rotate by 180 in either way, you will get to the same point. If we now have a crystal, then we have symmetry properties. So many orientations here are actually ambiguous. If you rotate a crystal with a two-fold symmetry by 180, it will look the same. So this orientation space will actually shrink. For example, let's take again this example of barium carbonate. This orientation space, what we call fundamental zone, which contains no ambiguous orientations, will only be like 180 wide here. And then if we have different kind of symmetries, this fundamental zone will have even different shapes. So in this case, we have just a single two-fold symmetry. So we have the 180 here, but it shrinks like this. 6 will even shrink it more. And then if you have secondary axis, it will also change the shape in the other directions. So this is very important because the smaller the orientation space, the less parameters in the end we will have to if we want to determine orientations or distributions, as we see a bit later. So to describe texture then, numerically and quantitatively, we need to define a statistical function, which is usually called the orientation distribution function. And here I demonstrate this by showing these three scenarios. So we have a polycrystalline material, and in the first case, all the axes of the crystallized point in the same direction. In the second way, we have this preferred orientation, but we have a distribution around it. In the third scenario, it's just completely disoriented or randomly oriented. If you want to describe this by a function, so now again we have a two-dimensional case, it's quite simple. We just need to define an angle through, to a reference, for example here, and then we'll see that in the first case, we just have a sharp peak in a probability function where we have the angle on the x-axis, probability on the y-axis, a sharp peak here. In the second scenario, we have it's more spread out. It might look like a Gaussian or whatever function. And in the third case, it's just completely flat. We don't have any information about what orientation is more likely. Then So this in 2D, so it looks quite simple. In 3D, of course, we have to fill this orientation space that we just looked at before. So there's different way how to visualize an orientation distribution function, but you see already it's not easy to look at. So we have this representation with the grid, so we see actually what's inside, but the higher probability in this case would be represented by a higher density of points. Alternatively, we can do it with colors, but we don't see in the inside. And there's another possibility to represent it like this. So we take basically the center of the distribution, we do a stereographic projection, and then take the next slice, next. And so we can look at all of the angles at once. So yeah, this is a drawback of this representation, and we have a lot of information at the same time we have to look at, and you will see later how it becomes even more complicated. But for now, let's try to, let's first talk about the experiments, so in particular diffraction experiments. I will just shortly demonstrate how diffraction is orientation sensitive. So the experimental setup is quite simple. We have X-rays, preferably monochromatic, that come in. We put the sample here, for example. Let's look at a single crystal. And then we have a 2D detector that records the scattered beam. And we will, if we have a single crystal, we will have this characteristic diffraction spot on our detector. Luckily, we know how to model a diffraction pattern because it's directly linked to the crystal structure itself through this formula, which is structure factor. So basically, we need to know the positions of the atoms and their types, which come in here. And then if we do a Fourier transform of this, which is contained here, we arrive from the real space crystal structure to a reciprocally lattice. So in this, we have so the reciprocally lattice will reflect the symmetry of the crystal, and we have the no, sorry, this is the wrong image here. Sorry. So here again in 2D, for example, we have a reciprocally lattice like this, and then when we can when we do a diffraction experiment, we, however, do not observe this, but we have to do, for example, an Ewald sphere construction. So what we actually observe on the detector will be our reciprocally lattice cut with this sphere, whose diameter depends on the X-ray wavelength. And if a point lies on the sphere like this, for example here, we say it's in Bragg condition, and yeah, we will observe it on the detector. If now our crystal rotates, then also this reciprocally lattice will rotate, and for example, this will move out here, and another point might move into Bragg condition. So depending on the orientation of the crystal, we will observe very different diffraction patterns, and can therefore quite well determine the orientation of our crystal with diffraction. But now, as we want to do texture tomography, which means we don't want just the orientation of a single crystal, but we have a polycrystalline material, and we are interested in the local texture of inside of this material. So we do tomography, and just to give a short outline, so standard tomography illuminates the sample from one side. We have the X-rays, for example, traversing the sample, and we get a projection of everything that lies on the way of the X-rays. So of course, but here we have all the elements that are on the way overlapping. So to take this information apart, we can rotate the sample, and then if this is a scalar quantity that we record here, we can just back project these, and if we have enough angles collected, we'll get all the information about all the slices within the sample. However, in our case, we don't necessarily record the scalar quantity, but in each point, we will record a full diffraction pattern. And so if we have diffraction and tomography combined, there's a few methods already out there. So for X-ray diffraction tomography, for example, in this case, we are dealing with polycrystalline samples, but they have a random distribution, like a flat distribution of crystallites. Then we will get a diffraction pattern which is completely isotropic, and consequently, again, we have a scalar quantity, and we can reconstruct in the different parts of the sample, different phases, different crystalline structures. In the other extreme, so which would be 3D XRD, we have a sample with kind of large grains compared to the size of the X-ray beam. So if we have, so on the path of our X-rays, there's only a few crystals, and we will get a very spotty diffraction pattern, and and we can attribute each spot to a certain crystal orientation, and then if we rotate them around, this will again move in and out of Bragg condition, and one can pretty well determine the structures of all the orientations of all the grains in this sample. So this would be the other case where quite a large portion of the sample would have very well oriented, very narrowly oriented crystallites. So, but what we are talking about now for texture tomography, for texture samples, it will look more like this. So our diffraction pattern has no full rings, but also no spots, but we have these kind of arcs which reflect our texture. Our setup is still quite simple. We have our sample mounted here in the X-ray beam. We can scan in 2 directions, and we can rotate also in 2 directions. This technique was started off as tensor tomography. Is initially implemented for usage in SAGs. So this would be this part of the diffraction pattern where you can look at like nanometer to micrometer scale structures. It was later generalized to the wax regime. So this part where we have actually diffraction peaks and look at the crystalline orientation. And so the idea is that, yeah, as you see, these arcs here represent our sample, and from there we can reconstruct broader textures like you were talking about before. So the challenge here is that as these peaks are all smeared out, basically, or many peaks are overlapping, you can no longer attribute the peak to a certain crystalline orientation when you rotate the sample. And in general, this has a consequence that we also need to rotate around this axis, which has some big drawbacks for the experimental side, but which Tilman will talk about in the afternoon. So to model a diffraction pattern for with a texture, we have actually all the ingredients already that we talked about. So let's assume we have a certain orientation distribution function with a certain, and so in every point here corresponds to an orientation of a crystal. we know how to model a diffraction pattern for this crystal orientation. And if we do a sum of all of these possible orientations weighted by the orientation distribution function, we can arrive to a texture diffraction pattern. So this is the first part we need if we want to make a model for this experiment. The second part would be how to construct our sample. So in this case, we would just partition it into voxels. And in every voxel, we need to describe the ODF. Then we can, when we have a certain setup where we know the X-rays come from this side, for example, we can count, or we can attribute, we can find out which voxels lie on the way. We project this ODF through, we get a total orientation distribution function over for everything that lies on the way of the X-rays. And this, again, we sum over the single crystal diffraction patterns, and we get the diffraction pattern for this orientation. And then this has to be done for all the different orientations and all the scanning steps also. So, but we still don't know how actually we make an orientation distribution function, because as you can imagine, it's a three-dimensional object. It's not so easy to parameterize, especially if there's many orientations possible. So in general, there's several ways one can think about. The simplest would just be making bins of angles. So in this case, again, we have this kind of Gaussian function that is here represented by this texture. And so you can see in black the like true distribution, let's say, probability distribution, and in blue would be an approximation by just discretizing binning and taking this into the computer, basically. Yeah. Another way, what we are using in our model would be described by harmonic functions. So I'm sure you know, if you have like this Gaussian function here, you can approximate it also by a sum of sines and cosines. So you have these harmonic basis functions, and if you add enough of them together with different frequencies, you can, so which means you increase the order here. If you, in the first order, it just look like this, and as you go higher up, you will get closer and closer to this real distribution, and here, for example, at 10, we are already there, basically. So this is some advantages if you can model your texture with this function, because it drastically decreases the number of parameters. Basically, you need one parameter for each harmonic basis function. However, a drawback of this is, as you can see here, there's this oscillation around 0. So actually, you might have negative parts in your function. And if you go to sharper textures, you will need to include more and more orders. And usually this can scale quite rapidly and give you, again, a high number of parameters. What is very nice, however, even at very low orders, so you can see in the first order here, it obviously doesn't predict correctly this Gaussian function. It's much broader. However, the peak should be at the same position. So the preferred orientation can be rather well modeled already with a very low order of this expansion. So if we take this to 3 dimensions again, we need, of course, 3-dimensional basis function. And what we are using are hyperspherical harmonics. So again, the ODF is reconstructed in the same way. We have a sum of coefficients. We have here 2 indices and the hyperspherical harmonics. So n is the order of the hyperspherical harmonics. So the higher the order, the faster more oscillations we have in these functions, but this time in 3D, so they look kind of like this. You can imagine kind of like normal spherical harmonics, which you know from the atomic orbitals or even other applications. So these are actually representations in axis angle space, as we were talking about before, and these have some nice properties we can use for texture tomography. For example, we can there's a symmetrization procedure, which means we can combine from each order several of these suborders in a certain way, and we will get basis function that reflect that contain the same symmetry properties as the crystal itself, which means then we can reduce the orientation space to this fundamental zone. Then there's also a rotation matrix, like the Wigner-D matrix, basically, that can rotate these functions just by changing the coefficients, which is nice for us because we need to rotate our sample. And then also we can make a positivity constraint on this by using a kernel which was presented in this paper if you want to look at it. And you can see here, for example, if this kernel has one parameter, and here we have an orientation, a part of an orientation distribution function. We have some negative oscillations here, and if you increase the kernel, this becomes more and more basically flattened out and Yes, so let's go a bit deep on how we then model actually the diffraction patterns in. So we have a combination of several orders. If we do the sum over the lowest order only, for example, the 0th order is completely isotropic, we will get just an isotropic diffraction pattern, like a powder diffraction pattern, and then this is just to show you how we translate now from this representation to this representation, where we azimuthally bin and actually give the same weight for every angle on the diffraction pattern. So here chi would be the angle and q the distance from the origin. So we find our diffraction peaks here. And in this representation now we can very well see that that the higher orders have these oscillations in this angle, and we can combine different ones to produce all kind of different textures. So it's important to notice here these are not yet diffraction patterns. They have positive and negative values, but basically we have this 0 order, and which gives the baseline, and the other ones make it oscillate around, in azimuthal direction. Yes, so this is how we model a diffraction pattern, and then from the coefficients of these diffractlets, which correspond again to the hyperspherical harmonics, we can then conclude the 3D orientation distribution function, which we get from this. So this is just a last small excursion to pole figures, because as we saw, a 3D orientation distribution function is not so nice to look at it. So often textures are looked at by pole figures, which can look like this, for example. This is a palladium sample. So this, what this is, it actually comes out of an experiment where the first kind of texture analysis were done actually with this setup. So we have an incident beam. Here you have the sample, which is mounted here on this rotation stage. We can do the rotation around 3 angles, here, then here, and then another one here. So you can really explore different orientations, and you can have another rotation here, which gives you the Q value. So you can set this to a certain Q value that corresponds to a certain diffraction peak, and then if you rotate, get all the rotations of the sample, you can recover the pole figure. But of course, it should be actually the surface of a sphere, and this is circle, so how do we get there? So this is again a stereographic projection. We have this sphere, and if we draw, and this is the diffraction angle. If we draw a line here, and then from the opposite point here, then we can actually map this point and all points from the upper hemisphere here on this plane up there. So of course here is a circle and a line, but if you imagine another dimension around here, this will be a sphere, and up there is a circle. And what is actually this sphere here in our experiment? So again, we have the reciprocal lattice, and we draw a line wherever we draw a circle around a Q value where we find a peak, for example. So we would find maybe these two here, but if we have a texture sample, then we might have several orientations, and we find a spot composed of all these peaks that lie on this Q value. And then you can see there's different pole figures. You can explore. You can better visualize the texture. So every kind of texture gives you a certain fingerprint on this. Here you can see one for the silica vivaroid biomorph, which will reconstruct in the evening, in the afternoon, sorry. And with this, I want to conclude. I will just give you a quick overview again about this reconstruction workflow. So we have our experiment, and from these diffraction patterns we get here, from all the different orientations and translations, we want to reconstruct an ODF in each voxel of our sample. So here's where our model comes in. We define the coefficients of all the hyperspherical harmonics in each voxel. So for example, we make an initial guess, then we project. We get the coefficients that correspond to this path of the beam. This gives us on how we have to combine our diffractlets to make the simulated diffraction pattern. We compare this, and then if it doesn't fit, we refine our coefficients. Else we get to our solution of the orientation distribution functions. So with this, I want to give you just a few points of literature I've used. So the slides will be available to you later. And I want to thank everyone on my team who helped me to develop this model and constantly improve it. And also I want to thank people from the SRF who were always supporting us to test and provided us a really good setup. Then Britta Meyer-Helm-Curve, who made the biomorph sample, and for the hyperspherical harmonics expansion is Jeremy Mason, who did all the development and helped us very well implement it. Yeah, and of course, thank our sponsors for this workshop. This is the end of the first tutorial, and if you have questions, please